indexed files in Lucene. Now we are focusing on indexed files. An index file is a computer file with an index that allow easy random access to any record given its file key. Here you can see a detailed look inside the Lucene's index format. Here .fnm, the fields, stores information about fields here, and .tis, term infos, part of the term dictionary stores term info, and here .frq, frequencies, contains a list of docs which contains each term along with frequency, and .prx, positions, stores position information about where a term occurs in the index. Here in the inverted index, Lucene uses a well-known index structure called inverted index. Quite simply, and probably unsurprisingly, the inverted index is an inside-out arrangement of document in which terms take center stage. Each term refers to documents that contained it. Let's dissect a sample book data index to get a deeper glimpse at the files in the index directory. Regardless of whether you are working with a RAM directory or FS directory or another directory implementation, the internal structure is a group of files. In a RAM directory, the files are virtual and live entirely within RAM. An FS directory literally represents the index of a file system directory as directory. The compound file mode adds an additional twist regarding the files in a directory. When an index writer is set for a compound mode, the files are written to a single .cfs file, which alleviates the common issue of running out of file handles. Our summary glosses over most of the intricacies of data compression used in the actual data representation. This extrapolation is helpful in giving you a feel for structure instead of getting caught up with miniature, which again are detailed on Lucene's website. This figure represents a slice of a sample books index. The slice is a single segment. In this case, we have an optimized index with only single segment. A segment is given in a unique file name prefix _c in this case. Here field names .fnm. The .fnm file contains all the field names used by documents in the associated segment. Each field is flagged to indicate options that were used while indexing. Is it indexed? Does it have a term vector enabled? Does it store norms? Does it have payloads? In order of the field names, the order of the field names in the .fnm file is determined during the indexing and isn't necessarily alphabetical. Each field is assigned a unique integer field number. Each field is assigned a unique integer, the field number, according to the order in this file. That field number instead of string name is used in other Lucene files to save space. All terms, this is a term dictionary .tis or .tii file. All terms, tuples of fields, field name and value in a segment are stored in the .tis file. Terms are ordered first alphabetically. According to the UTF-16 Java character by field name and then by the value within the field. Each term entry contains its document frequency. The number of documents that contain this term within the segment. In this figure shows only the sampling of the terms in our index, one or more from each field. Not shown is the .tii file, which is a cross-section of the TIS file designed to be kept in the physical memory for random access to the TIS TIS file. For each term in the TIS file, the the .frf file contains entry for each document contained in the term. Here in our sample index, 2 books have the value JUnit in the content field. Term frequencies. The term frequencies in each document are listed in the .frq file. In our sample index, that for example ant in action document ID 5 has the value JUnit once in the content field. JUnit in action second edition has the value JUnit twice, provided once by the title field and once by the subject field in this example. Our contents field is the aggregation of title, subject and author. The frequency of a term in a document in a document factors into score calculations and typically boosts a document relevance for higher frequencies. For each document listed in the .frq file, the positions.prx file contains entries for each occurrence of the term within the document. The term positions, the .prx file lists the positions of each term within a document. The position information is used when queries demanded it, such as praise queries and span queries. Position information for tokenized fields comes directly from the token position increment designated during analysis. This file also contains payloads, if any. In this figure shows 3 positions for each occurrence of the term JUnit. The first occurrence is in document 5 in position 9. In the case of documents 5, the field value after analysis is Ant Action, Apache, Jakarta, Ant Build, Tool, Java, Doc Development, JUnit, Eric, Hatcher, Steve, Logan. We use the standard analyzer, thus stepward in Ant in action, for example, are removed. Document 6, JUnit in action, second edition has contains field containing the value JUnit twice. Once position 1 and again position 3. Stored fields. When you request that a field to be stored, field.store.ts, it is written into two files, the .fdx file and the .fdt file. The .fdx file contains simple index information which is used to resolve document number to extract position in the .fdt file for the document's stored field. The .fdd file contains the contents of the fields that were stored. Term vectors. The term vectors are stored in three files. The .tvf file is the largest and stores specific terms stored alphabetically and other fields. Other frequencies plus the optional offsets and positions for the terms. The .tvd files list which fields had term vectors for a given document and indices byte offsets into the .tvf file so specific fields can be retrieved. Finally, the .tvx file has index information which resolved the document numbers into the byte positions in the .tvf and tvd files. Norms. The .nrm file contains normalization factors that represent the boost information gathered during indexing. Each document has one byte in this file which encodes the combination of documents boost, that fields boost, and normalization factor based on the overall length of the content that in that field. Deletions. If any deletions have been committed to the index against document content in the segment, there will be a .del file present, name _x_n.del, where x is the name of the segment and n is the integer that increments every time new delete are committed. This file contains a bit vector that set for any deleted documents. Here you can see the index structure in here. Here the index an index is basically a set of documents that are to be searched. The index may be composed of multiple sub-indexes or segments. Each segment is a fully independent index which could be searched separately. Fields. When a document is added to an index, different sections of the document are identified and given a common name called fields. For example, document title, document body, hyperlinks, the document URL, etc. Terms. The words in the field are extracted and are stored in the index as terms. A term basically a string extracted from the document. The same string in two different fields is considered different term. Terms are represented as a pair of strings. The first naming the field and the second naming the text within the field. Stored or indexed. The Lucene fields may be stored, in which case their text is stored in the index literally in a non-inverted manner. Fields that are inverted are called indexed. The fields may be both stored and indexed. tokenized and or non-tokenized. The text of the field may be tokenized into terms to be indexed, or the text of a field may be used literally as term to be indexed. Most fields are tokenized, but sometimes it is useful for certain identifier fields to be indexed literally. Lucene uses file extensions to identify different parts of the index. Here you can see the index structure. Here we are considering Lucene 3.4. Here segments are in index. Segments consists documents here. Documents are in segments. Here the fields are in a document, and here the terms are in field. Here you can see the now we are considering field information .fnm. Field info file with the suffix fnm records the index time attributes and field names for every field. Fields are numbered by their order in this file. Thus the field 0 is the first field in the file. Thus the field 0 is the first field in the file. Field 1 the next, and so on. Note that the like document numbers, field numbers are segment relative. Here you can see fnm version vint indexes version from 2.9 to 3.3 is -2, and indexes version from more than 3.4 plus is -3. Next you can see the field count vint, and next field name field bits. Here field name is string. In this this section consists of field name string and field bits byte. Here the bit 8 is 1 equal positions are omitted for the index field. Bit 7 1 equal term frequencies and positions are omitted for the indexed field. Bit 6 1 equal payload are stored for the index field. Bit 5 the 1 equal norms are omitted for the index field. Bit 4 1 equal terms offsets are stored with the term vectors. Bit 3 1 equal term positions are stored with the term vectors. Bit 2 with term vectors equal 1 and without term vector equal 0. Bit 1 indexed field equal 1, non-indexed field equal 0. So this bit 8 to bits 1 are in field bits byte. The field name string and field bit string are in this section. Here you can see stored fields. Stored fields are the original raw text values that were given in Lucene. This is not really a part of inverted index structure. It's simply a mapping from document ID to stored field data. Stored fields are represented by two files. The field index or FDX file that contains for each document a pointer to its field data. The field data or FDT file this contains the stored fields of each document. Here you can see the field index of FDX file .fdx. Here the offset equal doc id multiplied by htail u int 64 size. Here the field value position here the field value position segment size. Here the field value position u int 64 doc id is field value. It is connected to field data or FDT file. This should be FDT here. Here you can see document field data segment size here, and here the before that here you can see field count v int and another field, and then here you can see field number v int, and in this section consists of field number v int and bits v byte, and it consists bit 8 bit 8, and here the bit 7 to bit 6, so here bit 7, and here the bit 6 to and bit 5 and bit 4 is 001 value is an int, and 010 equal value is a long, 011 is equal value is int as float, and 100 the value is long as double. The bit 3 is in bit 3 one equal field has compression option enabled, only available for version less than or equal 2.9.x. Bit 2 one equal field contains binary data. Bit 1 tokenizer field equal 1 and non-tokenizer field equal 0. So it will be here bits and bits byte. Here the value string or binary value or int long depending on bits 4 to 6, with the binary value here value size v inc. Here the here the value size so binary value, the value size v int, and byte is value size. Here the field name bits and value here with the field count here, and then this section represents this area, and then the document field data segment size here. Now we are considering here you can see the term dictionary. The term dictionary stores how to navigate the various other files for the each term. At simple high level, the term dictionary will let you where to look in the FRQ and PRX files. For further information related to that term, terms are stored in an alphabetical order for fast lookup. Further, another data structure, the term info index, is designed to be read entirely into memory and used to provide random access to the TIS file. Other bookkeeping, skip test. Skip list and index intervals also tracked with the term dictionary. Term infos.tis. The term infos file.tis contain all terms in a segment ordered by field name. Then the value within the field. It also contains a document frequency for each term. Inverted index, so how many documents contain that term. Term info index TII .tii. This contains every index interval entry from the TIS file along with its location in the TIS file. This is designed to be read entirely into memory and used to provide random access to the TIS file. The structure of this file is very similar to the TIS file, with addition of one item per record in index delta. Index interval. In order to accelerate the searching of a term, Lucene uses multi-level skip list. The index interval is the interval at which the terms are saved in the .tii file. For example, assuming index interval equal 4, the dictionary index TII file will save 4th, 8th, 12th term, which can speed up the dictionary lookup in TIS. Skip interval. Skip interval is the fraction of term docs stored in skip tables. It is used to accelerate term docs .skip to int. Larger values result in small indexes, greater acceleration, but few accelerable cases, while smaller value result in a bigger indexes, less acceleration in case of small value for max skip levels, and more accelerable cases. Max skip levels in the max number of skip levels stored for each term in the .frq file. A low value result smaller indexes but less acceleration. A larger value result in slightly large indexes but great acceleration. See format of .frq file for more information about skip levels. Prefix length. The term text prefixes are shared. The prefix length is the number of initial characters from the previous term, which must be pretended to a term suffix in order to form the term's text. Thus, if the previous term's text was born, then the term is boy. the prefix is prefix length is 2 and the suffix is y. Document frequency, docfreq, is the count in of the document which contain the term. Frequency delta, freq delta determines the position of this term term freq within the .freq .frq file. In particular, it is the difference between the position of terms data in that file and the position of the previous terms data, or 0 for the first term in the file. Proxy delta determines the position of this term position within the .prx file. In particular, it is the difference between the position of the terms data in that file and position of the previous terms data, or 0 for the first term in the file. Skip delta determines the position of these terms skip data within .frq file. In particular, it is the number of bytes of the term freq and that the skip data starts. In other words, it is the length of the term freq data. Here you can see the term infos .tis. Here the TI version, uint 32, term count uint 64, index interval uint 32, skip interval uint 32, then max skip levels uint 32. Here term info, and then after gap term infos there. Here index intervals, one index interval here and then another index interval. Here this is index interval. Here term infos, term count. Term info consists of term, doc frequency, vint and frequency delta vint, proxy delta vint, and skip delta vint. Term consists of prefix length vint, suffix string, and field name vint. The term info index .tii, TI version uint 32, index term count uint 64, index term count equal term count divided by index interval. Index interval here term count L, index interval int 32, then the skip interval int 32, max skip levels int 32, term index and term index, and there are term indexes, and this is term index count from this area. Term index consists of term info and index delta or v long. Here the term index is connected to term info here. Here the term index is connected to term info here, and term index connected to term info here. So term indexes are connected to term infos in term infos. Now here you can see term frequencies .frq in Lucene 3.4 here. The .frq file contains the list of document which contain each term along with the frequency of term in that document. This file contains the term posting list. This file contains the term position list asterisk term count entries. Each entry is a posting list corresponding to a term. Each posting list consists of a turn frequency and a skip list. Term frequency consists of a list of doc deltas and the number of times this term occurs in that doc. The doc delta encodes both the document number and the frequency. In particular, doc delta divided by 2 is the difference between this document number and the previous document number, or 0 when this is the first document in a term freq. When doc delta is odd, the frequency is 1. When the doc delta is even, the frequency is read as another vint. If omit tf equal false, store the term frequency. For example, if the term occurs once in the document 7, doc id equal 7, the freq equal 1, and 3 times the document 11, doc id equal 11, and freq 3, we would get the following sequence of vint 15, 8, and 3. Here's how it is calculated. In order to save space, Lucene does not store the doc IDs as is. Instead, it calculates the delta as a delta. Doc ID delta equals 7 and frequency equal 1. Doc ID delta equal 4, frequency 4, 11 minus 7, and frequency equal 3. For this first term, since the frequency is 1, the frequency information is encoded in the delta itself. Doc ID delta equals 7, and the binary is 0000111. Since we want to store the frequency of 1 in doc delta, the last bit of the doc delta is 1, doc ID is odd, so we know that the frequency is encoded in the doc delta and freq equal 1. For the second term, since the frequency is more than 1, we use the separate vint to calculate the frequency. Doc ID delta equal 4 in the binary 00000100. Since we want to show the following int is for frequency and not another doc ID, we need to make the last bit 0. Then shifting left for and 1 by real frequency equal 3 then. So to get the sequence, doc delta equal 15, doc delta equal 8, freq 3, namely sequence 1583. If omit tf equal true, skipping storing term frequency. If the omit tf were true, it would be this sequence of vint instead 7 4. If we omit term frequency, then all we are storing is the doc deltas. The doc deltas are therefore doc id 7, doc id 11 equal to doc id 7, doc id 11 minus 7 is 7 and 4. Skip data. The skip data contains a set of skip lists that allow us to find term frequency, doc delta, FRQ, freq quickly, number of skip levels in skip data equal num skip levels, equal min skip data equal num skip level equal mint max skip levels flow log doc divided by log skip level, doc frequency equal doc count that contains the term item, number of nodes in and each skip level equal doc freq, number of nodes in each skip levels equal doc freq divided by skip interval to the power level plus 1, level equal level greater than or equal 0. All the skip levels are applied are appended together preceded by the skip level length. The last level does not need skip level length since there are no more levels below it, so it is skipped. All skip datum in all levels except the last level have a skip child level PTR, which point to the next skip level. Each skip datum skip node contains the following information: document number, payload length, freq skip, proxy skip, and skip child level PTR. Here you can see term frequencies.frqs file. Here the term frequent skipped and skip data with term count here, and here the this one consists of term freq, doc freq, and here the skip data. Here the term freq consists of doc delta vint and frequent, then frequency vint. Here the skip data consists of skip level, skip level length and skip level, num skip level -1 and skip level and skip datum. Here the skip level length vint and skip level, and it's connected to a skip level and skip datum here. Doc freq divided by skip interval to the power level +1 here. Here the skip level and skip level is connected. This is skip level here. Here the skip datum. It consists of doc skip vint, payload length vint, is freq skip vint, proxy skip vint, skip child level pointer vlong, and here it's connected to here the skip data. Here the you can see the frequencies file with the skip list here. For example, if the skip interval is 4, equal max skip levels 2 and doc frequency is 35. The skip level 0 has 8 skip data entries. equal 35 divided by 4 to the power 0 plus 1, containing the third, 7th, 11th, 15th, 19th, 23rd and 27th and 31st document numbers in term fix. Skip level 1 has 2 skip data entries equal 35 divided by 4 to the power 1 plus 1, containing the 15th and 31st document numbers in term fix. Thus for skip level 4 and when there are 35 documents, skip level 0 should include documents 3, 7, 8, 3, 7, 11, 15, 19, 23, 27 and 31, and skip level 1 should include 15, 31 documents. But in the real implementation we store the previous docs as shown here. Here you can see docfreak 35 and skip level 4, and this is doc list, and here the skip level 0 and here skip level 1. Here the term here the frequencies dot frq, term freak skip data term count, here the freak term freak and skip data, and here doc freak, and this is a term posting list. Here the term freaks are there, and in the end here the skip data, and term freak has doc delta vint and frequency vint term freak, and here the skip data skip level length skip data datum equal 14. Here the skip datum equal 30, skip datum 2, skip datum 6, skip datum 10, skip datum 14, skip datum 18, skip datum 22, skip datum 26, skip datum 30. Here mappings, and skip datum 2 here. And here skip level 1, and here skip level 2. Skip level is equal 0 here. Here the skip level 22 skip datum doc skip vint, payload length vint, freak skip vint, proxy skip vint, and skip child level pointer vlog. Here the now we are considering position location data.prx. The .prx file contains a list of positions that each term occurs at within the document. If omit tf is set to true in a field, no entry for that term will be stored in this file. If the omit tf is set for all terms, then the .prx files will not exist. The position delta is the is the difference between the position of the current occurrence in a document and the previous occurrence, or 0 if this is the first occurrence in the document. For example, term positions for a term which occurs at the 4th term in one document and as the 5th and 9th term in the subsequent document, the document would be the following sequence of vint 454. Payload in Apache Lucene is an arbitrary byte array stored at a specific position. That is a specific token divided by term in the index. A payload can be used to store weight for specific terms, so things like part of speech tags or other semantic information. Payload length is the length of the payload data. If there is no payload length but the payload data is found, its length is the same as the previous payload. Position file.prx, here the term positions, term count. Term positions consist of here term positions, here the positions, here the position doc freak, and position consist of positions consist of position, here the position freak. Position consists of position delta, vint, and payload, and payload consists of payload length, vint, payload data, bytes, and here the frequencies file.frq, skip level length. This is skip level 1 here, skip level datum 14, skip level skip datum 30, and here the skip level 0 as an example. Skip datum 2, skip datum 6, skip datum equal 10, skip datum equal 14, skip datum is equal 18, skip datum is 22, skip datum is 26, skip datum is 30. Here the in this example here the position, this position is connected to skip datum 2, and this position connected to skip datum 6, and sorry, this skip datum 2 is connected to skip positions here, skip datum 6 position is connected to position here, skip datum is 14 is connected to position here, and here the skip datum 14 is connected to skip datum 14 is here, and skip datum 30 is connected to skip datum 30. Here you can see the .kdd in filed in Lucene 8.6.0. The data structure of .kdd is here. Leaf node data describe the information of a leaf nodes. You can see there is only leaf node data in .kdd file, and the default maximum number of points in each leaf node data is 512 and 512. Here you can see the .kdd file structure, header, then fields, then footer. The field consists of left node data, sorry, leaf node data, and leaf node data, and the data segments. Here you can see a leaf node data. The count describes the number of points in leaf node data. Doc IDs describe the set of document IDs which point in a leaf node data belongs to. Point values describe a set of point values. Each point value is split into point values describes a set of point values. Each point value is split into two parts: common prefixes and block packed values. Here you can see a leaf node data consists of count, doc IDs, and point values. Here you can see the common prefixes. Common prefixes describe the set of common prefixes with each dimension. Length value, the value describe the common prefix value with the byte, and the length means the length of a common prefix value, number of bytes. Here you can see common prefixes consist of dimensions, first, second, n dimension, and each dimension consists of length and a value. Here you can see here .kdi in Lucene 8.6.0. The data structure of .kdi file is here. Here the packed index value describes the information of all inner nodes, also known as branch node. Inner node has 4 types of data structure according to the position of in KD tree and its subnode. Right node has leaf child. Inner node, that is the right that the inner node is the right node of its parent node, and its child node are leaf nodes. Right node has not leaf child. The inner node is the right node and its parent node, and its child nodes are not leaf nodes. Left node has leaf child. The inner node is the left node, and its parent node and its child node are leaf nodes. Left node has not leaf child. The inner node is the left node and it's of its parent node, and its child nodes are not leaf nodes. Root node as the inner node and it belongs to right node has not leaf child. Here you can see it consists of this .kdi consists of header and fields and footer. Each field consists with packed index value. Here you can see right node has not leaf child. Here the left leaf block FP describes the pointer where the position of the leftmost node, leaf node of the current inner node in the .kdd file is. Code describes the metadata about inner node, such as split dimension or byte per dimension, how many bytes each value in each dimension takes. Split value, in this stage the constructing a KD tree, that set of points in inner node will be split into 2 subnodes according to split value, which is a value of one of the dimension. Left num bytes describe the total size of one inner node's left subtree. Here inner node has not left child, consists with left leaf block FP, code, split value, and left num bytes. Here you can see right node has not leaf child. Left is in the here the left leafed block FP here the left leaf block FP code and split value describes the same meaning. Right leaf block FP describes a pointer where the position of the right leaf node of the current inner node in .kdd file is. Here the right node has left child, consists with left leaf block FP, code, split value, and right leaf block FP. Here you can see left node has leaf child. You can see the code, the split value, and right leaf block FP describe the same meaning. The left node has leaf child consist code, split value, right leaf block FP. Here you can see the left node has not leaf child. Code, split value, and left num bytes describe the same meaning left node has not leaf child consists code split value left num bytes. Here the you can see the here you can see the KD tree and index values, index file. Inner node in a KD tree would be stored in .kid file as below. KDI file as below. Here you can see the root node and it's connected to inner nodes, and this node is connected to other inner nodes, and this is these are leaf nodes. Here the root node is connected to right node has not leaf child. Then the this inner node is connected to left node has not leaf child. This inner node is connected to left node has leaf child, and this one is connected to right node has leaf child, and this inner node is connected to right node has not leaf child. Here the left node has leaf child, and the right node has leaf child. Here the this section makes a packed index value in .kdi in packed index value which is a field in .kdi file. Here you can see header and fields and the footer. Here you can see the leaf node in leaf node in .kd tree would be stored in kdd file as below. As here you can see a root node, and you can see inner nodes here, and then you can these are leaf nodes here. Here this leaf node is connected to left node data, and this one is connected to left node data. Leaf node, sorry, this one is connected to leaf node data, and this is connected to this leaf node data, and these leaf nodes are connected to leaf node data here, and this segment is this segment is a field in .kdd file. You can see header here and fields here and footer here. Here you can see the left num bytes. The left num bytes describe the total size of one inner node's left subtree. It makes a reader can skip to the position of inner node's right node in .kid file, and its left node is just in the next position. Here you can see a root node, and these are inner nodes, and you can see leaf nodes here. Here the root node is connected to left node has not leaf child, and it consists of left leaf block fp code split value and left num bytes. Left num bytes are here there here. Here the this node is connected to leaf node has not leaf left node has not leaf leaf child. This one is connected to this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child, and this one is connected to this inner node is connected to right node has not leaf child, and this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child. And here the left num bytes is covered this size, the left num bytes here for the tree here. Here you can see the root node is connected to right node has not leaf child, and this inner node is connected to left node has not leaf child. This consists chord, split value, and left num bytes. So it's covered this left here the left num bytes here, this section, and here the inner node is connected to leaf node has leaf child, left node has leaf child, and here this inner node is connected to right node has leaf child, and this one inner node is connected to right node has not leaf child, and inner node is connected to left node has leaf child, and inner node is connected to right node has leaf child. Here you can see left leaf block FP and right leaf block FP in Lucene 8.6.0 here. By left leaf block FP and right leaf block FP, leaf nodes can be positioned in .kdd file. Here you can see the root node is connected to right node has not leaf child, and it consists of leaf left lead block FP, chord, split value, and left num bytes, and it is connected to then here the left leaf block FP is connected to here the left leaf node data here, and here the here you can see this inner node is connected to leaf node has leaf child, left node has leaf child, and is chord, split value, and right leaf block FP is connected to this one here, this leaf node data here. Here you can see the this inner node is connected to right node has leaf child, and here you can see left leaf block FP, chord, split value, and right leaf block FP. Here the left leaf block FP is connected to this leaf node data, and here the right leaf block FP is connected to leaf node data here. Here you can see the .kdm is the data structure of .kdm file. Data structure of .kdm file is here. You can see here the -1 is a fixed padding value. In this stage, the reading in the stage of reading .kdm file, it has a mark. It as a mark means means all fields has been read. Here you can see a .kdm file consists of header and fields and -1 here, and KDI file length and KDD file length and footer, and field consists of field number and index. Here you can see KDI file length and KDD file length. In this stage of reading .kdm index file, KDI file length and KDD file length used to validate KDI and KDD files such as truncated file or file too long. Here you can see the .kdm file. It consists of header and fields and -1 KDI file length and KDD file length and footer. Here KDI file length is connected to a KDI file length here. Header, the length of with header and fields and footer here in KDI, and KDD file length is connected to the KDD file length in file length in .kdd with header, fields and footer. Here you can see in index. Here you can see the index in .kdm. Here you can see the header. It consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start fp, index start fp. Here you can see the index in .kdm here. Here num data dims describe how many dimensions we are storing at the leaf data nodes. Here the num index dims describe how many dimensions we are indexing in the internal nodes. Here count per leaf describe the maximum number of points in each leaf node. Byte per dim describe the number of bytes per dimension. Num leaves describe the number of leaf nodes. Min packed value describe the minimum value for each dimension, and max packed value describe the maximum value for each dimension values. Point count describe the total number of index points across all document. Doc count describe the total number of documents that have index at least 1 point. Length describe the size of packed index value. Data start fp describe the pointer where the beginning position of current field data in .kdd file is, and index start fp describe the pointer where the beginning of position of current field data in .kdi file is. Here you can see the KDM .kdm, and it has header, fields and -1 .kdi file length, .kdd file length and footer. In the field you can see the field number and index here. Index consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value,
point count, dot count length, data start fp here with is connected to .kdd here, and here indexed start fp is connected to .kdi here, and here the .kdd has a header, fields and footer. Field has left leaf node data segments. Here the index start fp is connected to .kdi. Here it has header, fields and footer, and field is a packed index value. Here you can see .kdm complete data structure here now. Here the .kdm consists of header and fields, -1, kdi file length, kdd file length and footer. Field consists of field number and index consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, dot count, length, data start fp and index start fp. Here you can see the .kdd complete data structure. Here you can see the .kdd has a header, fields and footer. Field has leaf node data segments. Leaf node data consist count, doc IDs and point values. Point value consists common prefixes and block packed values. Common prefixes consist dimensions, first, second, and in dimension here. Each dimension consists of length and value. Here you can see .kdi complete data structure. Here you can see the .kdi. It has header, fields and footer. Field is a packed index value, and packed index value consists of right node has not leaf left leaf child and etc. Then left node has not leaf child, left node has leaf child, right node has leaf child, right node has not leaf child, etc. Then right node has leaf child. Here you can see the representation of inverted index. A linear scan is a simple process sequentially going through each line of in the system and checking its parameter, that is condition in a given query. This is precisely how Unix grep command works, and it also works fairly well with the wildcard and regular expressions. If the size of data set being searched size is not too large, and then the hardware being used is reasonably powerful, linear search is the simplest way. However, linear search starts showing performance degradations beyond the million median size document. The world around us is too experiencing an information explosion. In fact, the amount of data that needs to be processed to extract relevant information is quadrupled over last 10 years thanks to the advent of connected world, handheld devices and IoT. Linear search cannot be scaled to meet those needs, and so we need something more sophisticated and performant than that can handle massive dataset while still providing relevant result at reasonable speed. Linear searches also limit what kind of queries can be answered. For example, there is no way to define query that seeks close matches of a given pattern. Suppose, for instance, that we search for document with the words flower and sunshine within a proximity of 3 words in a document. Doing so with a linear search is impossible. So also there is no notion of rank result, that is a given query, the result is either a match or not for a linear scan. If we want some sort of ranking, we cannot use the linear scan. An inverted index here is a data structure used to store data in an inverted manner. That is, terms are mapped according to mapped to documents in which the terms appear. Any unique term appearing in any document is made part of the inverted index. As shown in this figure, this data structure proves useful for answering questions like find me the document containing term 1 in an optimized manner. As you can see, a single term search is a constant time operation. To create an index file, fields within the document are first split and tokenized. A sorted list of all the unique terms is created. And the documents that contain the corresponding terms are populated. While being fast for a single term query, inverted indexes can also answer an important class of questions, similarity queries. Here you can see a term and document IDs, here book 1, book 2 and book 3. Here you can see Lucene index structure. The on-disk representation of Lucene index is optimized to be sufficient in reads and writes, and it allows searches into required areas of the index. At the heart of the Lucene lies the Lucene index file format. Post-Lucene 4 formats are pluggable using custom codecs and codecs. However, the default file format is what is published on Lucene's official website and what is in the official. Referring to this figure, the basic component to start defining are as follows. Field definitions. Field definitions are stored in an independent file named field infos with the extension fnm. With version 4.0 from the official definition, field infos.fnm is going to fnm version, fields count, then field name and field bits, field counts. Here you can see the term dictionary. The term dictionary is represented by two files. The term infos, the TIS file hold the metadata about the term, such as term name, skip information, and document frequency. That is the count of document that hold the term. The TIS file also hold the useful information that helps the Lucene to build structures for more optimal access of relevant document for a given term. Lucene uses skip data structures internally to make access faster. And this TIS file holds data to help build this structure. In addition, metadata such as term frequencies in this file allows allows faster access to other files. The term infos index file, the TII, holds metadata to allow random access to the term infos file. The frequencies file extension .frq maps documents to a term. uh, uh, that is it contains a list of all documents that contains a term present in the terms dictionary, along with the frequency of each term in the document. Positions file .prx positions file, the extension .prx represent the list of positions at which each term occurs within the document. Here the field definition .ffnm file is connected to a posting list .tis. It is connected to a frequency .frq, and it is connected to a position here, the .prx. As we can consider this as an example, here the interface path, an object that may be used to locate a file in a file system. It will typically represent a file dependent file path. Here you can see the class files. This class consists exclusively of statics methods that operate on files, directories, so other typical types of files here. This interface path is in module java.base and package java.nio.file. As an example too, we can consider .nfm. The field names are stored in the field info file with suffix .fnm. 3, we are considering class index file names in package work.apache.lucene.index. This class contains useful constant representing file names and extensions used by Lucene, as well as convenience method for querying whether there are file name matches and extension, as well as generating file names from a segment name, generation and extension, file name from generation, segment file name.